cosmology in EFT in cosmology. Please start.
Okay, thank you. Welcome back. I'll just turn my timer on here. All right. Excuse me. So, got a long road today. Hopefully we'll get through everything, but if not, then the slides will be there, and feel free, as usual, to ask questions. So there was a good question yesterday about the Hubble tension, and so it made me realize that in preparing these slides, one of the advantages of slides as opposed to a blackboard is you can put in data, and so so I've been saying things like the equation of state of dark energy is W equals -1. But I haven't been showing you the evidence for that. So I'm going to just very quickly, before I start, recap some of the things I've said to show you the evidence for them. And so the first one these are measurements of the Hubble expansion rate is the vertical axis, and across the bottom is the fraction of the energy density in the universe that's in non-relativistic matter. And the microwave background plus basically the microwave background puts you into these ovals, and the various ovals just depend on which combinations of observations that people use. And then the strip, the horizontal strip, is measurements of the same expansion rate based on measurements closer to us than the microwave background. So the supernova, these are actually based on Cepheids. So you have a distance ladder where you measure, you infer how far away things are because you think you identify objects whose brightness you know. And in this particular, the one that disagrees significantly is based on Cepheid variable stars. And so there's a controversy about whether or not the errors are being quantified properly in one of these two measurements. But you see that they're in tension with each other. That's what was being alluded to. And the question now is that physics, or is that just measurement error? I told, we talked about the equation of state for the vacuum. It was pressure was equal to minus energy density, and that's normally parameterized by the ratio, which is calling W here, which is -1 in that case. And this is a measurement of what what they did was they assumed that this equation of state parameter W was a linear function of the scale factor. So W naught would be the value it has now, and then WA is its derivative now. And then they see how that would have changed observations, and so where the lines meet in the middle here. Let me somehow my screen has changed, so I don't have the here we go. So where the screen meets in the middle here is what I've been telling you the equation of state would be for the vacuum, and the observations put you in these various ellipses depending on which ones you're using, which are the ones that are pointing you towards. They give you an idea of the accuracy with which you're being pointed towards the equation of state of the vacuum. I gave you a story last time about how we know that the space is flat. And that was because of this triangle that you can draw between us and the microwave background, all of whose sides you know, and the angle you know, but one of the sides you only really knew if you knew how big the universe was. So this side here required knowing the Hubble length. So let me show you the evidence for the flatness of the universe. So this is a plot of the vertical axis is the again, the fraction of the energy density that's non-relativistic matter. And the bottom is a measure of the curvature of space. If space has a curvature, it changes the Friedmann equation that gives us the Hubble scale. And you can write the contribution of curvature as if it was another contribution to the energy density of matter. And that's what's called omega k, that divided by the present day energy density. And so this is showing you the error ellipse you have to live in there, and the colors are showing you separately the value of the Hubble constant that you have to assume. So where you are on this ellipse depends on what Hubble constant you've used. And because I remember I told you that in that triangle argument, you need to know how far away the microwave background was. And the current value the best fit from the microwave background is 67 or something. So that's this area here. So that's what's putting us down here. And that's how you see that it's things look flat. That's the accuracy with which we know that things are looking flat. Excuse me. And then we talked about the power spectrum of the density distribution of galaxies. And I told you that it is parameterized phenomenologically as something which is a power law for small k, and then there's a change, a larger k, which describes this transition from the power law is kind of describing what's going on here for small k, but then the denominator is what turns you over and has you go down by it looks like the power law here is 1 over k to the 4th times the power law here is basically what that phenomenological description is saying. And I told you that the today's lecture was going to show you that the small k behavior is about the initial conditions, and then the turnover, the alpha and beta parameters are all about how gravity evolves in times that we can actually see, so the post-microwave background times. And I told you that I'm just showing you the numbers here. NS is 0.97. It's almost 1, but not quite. But I'm not really giving you a sense of the errors there. So this is showing you a better idea what the errors are. This is the top value is the best Planck collaboration value. You can see it's 0.9649 plus or minus 0.0042 gives you an idea how accurate it is. And the vertical axis in this plot is R, which is a variable we're about to run into. It's the ratio of the tensor fluctuations to the scalar fluctuations, which, as you can see from the plot, is consistent with 0 in measurements right now, to an accuracy of about 10. Actually, it's better than this. This is an old plot, but gives you an idea. When I tell you later on they haven't seen tensor fluctuations, you'll see this plot again. Okay. So those are gives you a better idea that there's a fit going on to a model which doesn't have a lot of parameters to it, and the accuracy with which these numbers are being determined is not. It has some precision. It's not like it's order. You can change it by factors of 5. It's happening at the percent level or less sometimes. So we were about to go through the story of describing how fluctuations evolve, and I'm trying to, in this story, give you the evidence that that picture of the distribution of galaxies, the power spectrum, is well described by gravity amplifying initial overdensities of, that were initially there in the distribution of matter. And we know that those initial overdensities were small because the microwave background shows us that they were 1 part in 10 to the 5 at very early times. And so the picture is that they are amplified by gravity, and what's the evidence for that? So to describe that, since we know that initially the fluctuations are small, we can do things, we can perturb around the homogeneous solution. And so that's where we were starting. That's where we were going when the last lecture ended. So we're solving Einstein's equations here, but we're taking the metric and the matter to be no longer homogeneous and isotropic, but that we're allowing there to be fluctuations. But we're imagining that those fluctuations are small. So the background values, the things that are denoted by an overbar, are the homogeneous things that we've been talking about till now, and the delta G and the delta T are the fluctuations. And there was a gauge invariance involved, and I kind of went through that. And there was the metric could be decomposed, but only 2 things were going to matter in the end of the day. The phi was what was playing basically the Newtonian potential, and h was describing gravitational waves. So the physical degrees of freedom of the gravitational field. Phi is a degree of freedom too, but it's not in the sense of like a particle degree of freedom. It's more phi is constrained by Newton's law, basically the Poisson equation. It tracks, del squared phi is related to the energy density, and so whatever the energy density does, whatever the fluid, the matter does, phi just follows it. But it's not like you have an independent wave in phi, the gravitational degree of freedom like you have in the spin 2 tensor fluctuations, what's hij here. And the last slide I showed you last time was telling you what happens when you linearize Einstein's equations. What's it look like, the evolution equations for those variables? H satisfied a wave-like equation, and then phi satisfied in the non-relativistic regime the Poisson equation, which is the Newtonian version of gravity, that if you solved del squared phi equals 4 pi g rho, you get Coulomb's, or you get Newton's law for phi. Phi will, for point source, phi will go like, g m over r when you solve that equation for a spherically symmetric source. But these two were supplemented by, that just says that phi is there's no time derivatives in phi. So it's just telling you that phi is constrained at any given time to be related to whatever the fluid's doing through rho. But we have to have the equations of motion for the fluid. And those are the usual ones for fluids. And the ones that you get relativistically become the ones that you normally use for fluids, the Navier-Stokes equations, because those equations are just really expressing conservation of energy and momentum and particle number. So these are the equations of motion for a fluid. The second equation is the energy conservation equation. Rho is, as usual, it's the energy density. V is the velocity of the fluid, and there's a preferred frame for the fluid, and that for us would be the one for the microwave background. And V will be the fluid motion relative to that frame. P is the pressure. Third equation is the momentum conservation equation. That's the Navier-Stokes equation. And the last one is the one that's describing how the temperature evolves. So this is the entropy conservation equation. And I'm assuming in writing it that whatever the evolution is, it's adiabatic. So we're not producing, it's reversible, basically, which is an assumption you can change, but it's good to, it's good, a good one. It's a good approximation for, in practice, what we're going to be looking at. All right, so now the goal is we want to solve these equations, and we want to start with the background solution, the one that was the expanding universe, and then look at the perturbations. And since I've got the non-relativistic equations here, and because the important parts of the story are happening in this gray band here, remember, here's the story, here's the history of the expansion history of the universe. So this is the logarithm of the energy density, and across the bottom is the log of the size of the universe. And we're here where the size of the universe is 1. And you remember matter falls like 1 over a cubed, the energy density does, and radiation falls like 1 over a to the 4th, and the vacuum doesn't do anything, it just sits there. And this is the point of radiation matter equality. And where I'm headed is a story which is going to be focused on this, the important interval is going to be between where matter and radiation have equal abundance and now. That's when the galaxies are going to form. And the microwave background, for comparison, was being emitted here at a redshift of about 1100. And in this region, we're dominated by non-relativistic matter, and we're going to be interested in the perturbations of that component of the fluid in particular. So that's the rho that we're talking about in these equations. And because we're in this regime, this is where a non-relativistic description will be the best. We could also do a non-relativistic description of the non-relativistic component of the matter in radiation domination. And I will mention that as we go by. But to do a proper job, you need to really think relativistically there. And it's also true that even in this region that we're interested in, if we follow scales that are large compared to the Hubble size, that's also a place where relativistic effects will be important, because the Hubble scale, the freezing of things is a relativistic effect, and non-relativistic physics won't capture that. So as long as we stay distances smaller than the Hubble size, and we do it in this interval here, and we focus on the non-relativistic degrees of freedom, we can use these non-relativistic equations, which are easier to solve. So let's just go through that. I'm just going to walk you through the solutions, because this is something you can do too. So, so what are we doing? We're solving these equations, the ones at the bottom here. And I'm going to first verify for you that there is a background solution, which is the expanding universe, which we did for the full-on Einstein equations, but you might want to see that again for the non-relativistic versions of them. Let me get rid of my laser pointer here. All right, so a background solution that describes an expanding universe is this one. The velocity will, the fluid velocity will be radially directed out, and the Hubble scale will appear as the proportionality constant. That's kind of the expression of the Hubble law, that everything is expanding. The velocities are proportional to the distance from any one observer. That solves the field equations, provided that the background density depends on the size of the universe inversely with the volume. So H here is, I'm thinking of as being A dot over A for some A, and for that A, rho has to go like 1 over A cubed, and that's kind of what non-relativistic matter did in relativity as well. Newton's potential just becomes what it has to be to have that density as a source. So it's radially pointed, basically. It's minus the gradient is what force will be, and that's a radially pointing in towards the origin force. So it's slowing down the expansion of the universe. And h, from the momentum conservation equation, h has to be proportional to 1 over, it's got to be 2 over 3t. And that's, again, what you would expect if h was a dot over a, and a was going like t to the 2/3, which is what I showed you in relativity matter-dominated universe does. So this kind of verifies that if you just take the equations that we had, plug those in, they solve the equations provided that these things are true. And so that's our background solution. That's our background expanding universe. And now what we do is we just expand everything in the small perturbations around that. So the velocity will be some change to the background velocity. And so on with the density. I'm going to allow myself to have an entropy perturbation, but I'm going to set it to 0 later on anyway. It's not going to play much of a role, but you don't need to do that if you don't want to. And now you just take the equations we had and which were nonlinear equations, which made them hard to solve, but now they'll be linear in the fluctuations because we'll throw away anything that's quadratic in these small changes. And this is what they become. So these are the same equations where I've now linearized in the delta quantities. And so they're recognizable. They're not that different from what they were. And so what we like to do is solve for the density perturbations. And what we're going to do is we're going to take the time derivative I guess what we're going to do is take the time derivative of the energy conservation equation, and we're going to take the divergence of the momentum conservation equation, and they're going to both involve the time derivative of the divergence of delta v, and we'll use one to eliminate that velocity, and we'll just get an equation involving just the density. And this is what we get when we do that. So we're going to they were first order equations. Now this is second order because we've eliminated the velocity. And it has the wave kind of form, right? It's got 2 time derivatives. It's got 2 space derivatives. There's the friction term because of the expansion of the universe. There's this piece to do with the gravitational, the fact that the background density is gravitating. And there's a source term, which is to do with the amount by which you're changing the entropy or the changing temperatures in your problem. And delta here is just defined, it's just delta, the change in density divided by the initial density. So it's a fractional change in density. And these coefficients c squared and c are just derivatives of the pressure with respect to the density or the entropy. So if you know the equation of state, you would know what these things are. And the interpretation of the c squared is going to be cs squared, is that's the speed of sound. Because this is a wave-like equation. It's going to be describing for short wavelengths, sound waves in the fluid, and that'll be the speed of sound for that fluid. We're going to go to momentum space because we can. The background was translation invariant, so we might as well do that. And so this bottom equation is one we want to solve. I'll rewrite it at the top again, same equation. I'm going to get rid of the source term usually, but in general, the solution to the equation like this will be a specific particular integral plus the general solution of the homogeneous equation where we get rid of the source term. So I'm mostly going to talk about the homogeneous solution. So the source term is not going to play any real role. And so you see that this really is looking like a wave equation with with some friction attached to it. And so if we take this term, sorry, you can't see my, put the laser pointer on. If we take this term, the k squared term, and we imagine the k is large enough, so the wavelengths are short enough that it's bigger than this term, then this really is the wave equation. And you can solve the solutions in that case have this damped form. And they're oscillatory, but then they have a prefactor, which goes like 1 over the size of the universe to some power. And that shows you that the expansion of the universe is damping these waves out, but they're basically behaving like waves. This will be something which works at short wavelength, and we had to check that we were at short wavelength compared to the Hubble scale. The scale, the condition that the k squared term dominates is the condition that k over a squared, which is a physical thing, that's got to be bigger than this. This is this length scale is important, and so that's why it's got a name. It's called the Jeans scale. This is the Jeans wave number. So the wavelength that goes with that would be the Jeans length. And you see that it's parametrically large compared to the Hubble scale because the speed of sound is small compared to 1, the speed of light for non-relativistic fluids. And so speed of light would be 1 in the units we're using, and so cs squared is much, much smaller than that typically. And so this is a scale, we can satisfy this, we can make k over a squared bigger than this And that's consistent with k over a squared being bigger than h, because this is bigger than h squared. So far, that just shows you that the reality check, we got sound waves. But the interesting thing is this other limit where this term is smaller than this term. That's the case where you change the sign of this square bracket. And that's where the instability lies. I told you that gravity likes to amplify over dense regions, and here's where you see it in the equations. So when you've got a long wavelength mode, which is when k over a is small, it's got to be less than this scale. But it can't be less than the Hubble scale, because we don't trust these equations if we're less than the Hubble scale, because that's a long wavelength, a mode that's longer wavelength than the Hubble scale. But there is a regime where you can be less than this and bigger than the Hubble scale precisely because CS is small. So this thing is parametrically large compared to the Hubble scale. Here in this this last equality I've just used, we know what the Hubble scale is compared to rho naught from the Friedmann equation. And so you can see that there's an order one number here, but the important thing is that the speed of sound amplifies the size of this Jeans scale. So there's a regime in which this square bracket can be negative, and I claim that so that you can solve the equations for that case too. And this is what you get. There's two solutions again. Previously, we had two oscillatory solutions where the sign of the exponential changed, but now you get two power law solutions. One goes like t to the 2/3. One goes like 1 over t. It's a second order equation, has two linearly independent solutions. These are them. And you see that in cosmology, this one falls. And so it doesn't really matter if you start with a component of that second solution. You wait for a while, it's gone. And the important thing that will always be there at late times is this growing solution. So this growing solution is the instability. It's the thing that's showing you that that delta, if you start off small, is going to want to get bigger. As long as it starts, no matter how small it started, it's going to want to grow. And the important thing for what we're going to say later is how fast it grows. It grows like t to the 2/3, and in a matter-dominated universe, remember, that's the same dependence on time as the scale factor itself has. So that means that the amplitude of these waves is growing proportional to the size of the scale factor as the universe expands. That's the key thing we're going to need. This equation that we're looking at here, it also applies in the case of a radiation-dominated universe. If we're focusing on how waves move around in the non-relativistic matter during radiation domination, we can use this same equation. We just have to keep in mind that h now is a different function of a. If radiation is driving the Hubble scale, it's going to go like 1 over a squared rather than 1 over a to the 3/2. And so, when I derived the equations previously, one of the things we derived was that the density had to be matter-dominated. So if we go to a radiation-dominated universe, not all the equations are going to be satisfied anymore. The one that gave us the Hubble scale is going to not be true anymore. So we'll have to use the relativistic one for that. And that's the one that gives us the time dependence of, or the A dependence of H. But the specific equation that describes the evolution of the non-relativistic matter doesn't change. And so that's why we can still use this, even though we're stepping outside the domain of validity of the original discussion. And if you just solve this equation again in the same regime where this square bracket is negative, but now where H is the radiation dominated H, what you find is that there's two solutions again. But now the smaller solution, the one that falls, is actually just a constant. And the other solution grows, but it only grows logarithmically with A, as opposed to like a power of A. So it's much, much slower growth compared to a power law growth. So the lessons you draw from that discussion is threefold. There is an instability, like I told you, but it's only there if the following three things are true. So you had to be first looking at, or I'm going to do the second one first. You had to be looking at the non-relativistic fluid. I haven't actually gone through the other fluids, but if you check them, they're not unstable. The one I've showed you is the one that's really the instability. So you have to be looking at you have to have a non-relativistic fluid around, which we do. We have dark matter and baryons. The modes that are unstable will only be unstable if the universe is matter dominated. That's 0.3 there. And only the modes that are smaller than the Hubble scale in wavelength will be unstable. Once you're above the Hubble scale, I argued for you last time that things always like to freeze, and that's not in contradiction to what I showed you, because in that regime, when you're above the Hubble scale, you don't trust the non-relativistic derivation that I gave. So these three things all have to be true to get an instability, and that's what kind of puts us into a particular window in the history of the universe. And we know that once it's unstable, the modes grow proportional to the size of the scale factor. So now I want to use those three facts to show you why the power spectrum has the form it does. It's some power of k, which we can't determine from this, but the fact that for large k goes like 1 over k to the fourth times whatever was happening at small k, we can demonstrate as being a consequence of these properties. So let's think about how modes grow. So remember, a key observation is that wavelengths are expanding with the size of the universe, but they're not expanding with the same speed as the Hubble scale. And so, and in particular, during a radiation domination, the Hubble scale is growing faster than the radiation, than the size of the wavelengths is. So the red lines here are the wavelengths, the blue lines, the Hubble scale. So now there's going to be a particular one that crosses from super Hubble to sub Hubble at the epoch where radiation and matter have the same size, the radiation matter equality time. At that instant, there'll be one specific wavelength that comes across. I'll call that k star. And the ones that have a longer wavelength, so k is smaller, they're going to cross later because those are ones for which the length is larger. So that's going to be higher in the plot. And so they're going to cross the Hubble scale at a time which is later than radiation matter domination. So that means they will cross during matter domination because that comes later. And the same thing, if we look at a shorter wavelength mode, those will cross the Hubble scale earlier. And so they'll cross during the radiation dominated time. Now, the reason that matters is the ones that cross during matter domination, they're immediately free to grow because now they're unstable because it's matter dominated and they're non-relativistic, and they will grow by an amount proportional to the size of the universe. But the ones that cross during radiation domination, they only grow logarithmically. So they're basically stunted. They sit there until matter domination happens, and then they start to grow. So what we should expect is that the shorter wavelength modes that are crossing down here, they should be stunted compared to the ones that are crossing up here. And that's kind of why our power spectrum is going to turn over. And so I want to now show you that that predicts that it turns over by an amount which goes like 1 over k to the fourth. So let's just ask how stunted they would be. So what we do is here's the amplitude of a mode with momentum k. Here's one with momentum k, and it's k0. And I'm imagining k is one that's crossing during radiation domination, so it's bigger. So it's bigger than k star. And k naught is smaller than k star, so it crosses during matter domination. And I'm looking at the size of those fluctuations at a particular time a, let's say now. So what I'll do is I'll compare their size to their size when they cross the Hubble scale, because that's where they start to grow. And so a sub k is the size of the universe at the instant where that particular mode crossed the Hubble scale. And so, so we have both of them are the amplitude they had when they crossed the Hubble scale times something linear in a, because the instability is linear in a. But the one on the bottom starts from as soon as it could, and the one at the top can only start growing once radiation matter equality happens. So that's what a equals is. So if I just rewrite this numerator so that they both are doing what they would have done if they didn't have to wait, then we would have had this. And this is getting it wrong by this factor is different from this factor by this factor. So this is the amount by which the numerator has been stunted compared to the denominator. So what we need to know is how this depends on k. But we know that because a sub k is just the size of the universe when mode number k crosses the Hubble scale. So it's defined by the condition that k over a sub k is equal to the Hubble scale at that time. I'm making an argument that this factor here is 1 over k squared, basically. It's something divided by k squared. And the way we figure that out is we know that the definition of crossing the Hubble scale is that this is true. And so if I solve this for k, it says that k is equal to this. But I also know during radiation, or during matter domination, that a goes like t to the 2/3 and h goes like 1 over t. So that means that during matter domination, h goes like 1 over a to the 3/2. So that means this whole thing goes like 1 over root a. So that says that k is proportional to 1 over root a, or a is proportional to k squared. And so that's 1 over k squared. So that's why this factor goes like 1 over k squared. But we know, so that's what I've just shown you. But we know that the power spectrum is the square of delta. So that means that the power spectrum is going to go like 1 over k to the 4th. And that's why this side is going like 1 over k to the 4th times that side. So this shape here is explained by the dynamics of the gravitational instability, and this peak in the middle, this special value of k at the top, that's defined by the wave number that cross the Hubble scale at radiation matter equality. That's what determines that number. So by measuring where it is, we're learning, that's a test of the picture, because it's just showing you what the scales were that were crossing the Hubble scale at radiation matter equality. So the thing we don't know from this is what determines this power. Why was this linear in K as opposed to something else? Linear in K, a clue as to what's going on there is that linear in K is called a scale invariant spectrum. And that might be surprising, because you say, well, NS equals 1 doesn't look scale invariant. It looks like it depends on K. So the reason they call that scale invariant is that people are normally not so much interested in the density distribution. They're interested in the Newtonian potential distribution. So first of all, if I take the density distribution, this is the way we define the power spectrum, and was that we just Fourier transformed everything. But if I take, the d3k, it has got a factor of k squared dk in it. If I write that as k cubed over k, this is a scale invariant thing. I can do the angular integrals because everything's rotationally invariant. And so the angular integrals turn the e to the I kr into sine kr over kr. And so that's something which is scale invariant for small kr. So it's natural, if you're interested in tracking scale invariance, not to track p, but to track k cubed times p. So I'm going to call that delta, because that's the thing that would be k independent if things were scale invariant. Now this is still not scale invariant, because if p is linear in K, then delta will be quartic in K. But the thing that's scale invariant is not the density distribution, it's the Newtonian potential distribution. So the Newtonian potential in the metric, that's the thing that is actually the thing that you measure, because that's telling you how the light from the CMB redshifts as it climbs out of potential wells. It satisfies the Poisson equation says that del squared phi is equal to the density. So that means that in K space, K squared phi will be what we call delta. So if I do the same power spectrum for the Newtonian potential, it will be given, it'll have the K dependence that the density does divided by K to the fourth. And so since delta is K cubed times P, that means it'll be P divided by K. And so that means that for small k, the primordial form is for this variable is k to the ns minus 1. So if ns is 1, that is scale invariant. That's why people call that a scale invariant potential. So we're looking for something which would make the Newtonian potential scale invariant, but it's going to have to come from earlier times, because we've already processed through late times, and we've seen it's giving us a shape, but it's not telling us what's happening at small k. So now the final cosmology story is what's the story at earlier times, because that is a step beyond the normal hot Big Bang model. So the understanding where these primordial fluctuations came from is one of a class of initial condition problems that the hot Big Bang model has. They're not really problems in the sense that the hot Big Bang model describes nature very well, but you have to start with just the right initial conditions to make that work. So one of the things you have to do, besides having these primordial fluctuations with the right spectrum, is you have to have the temperature of the CMB everywhere the same. That's something which is an initial condition at the end of the day, because there's no dynamical reason why it would be the same. And it has to be true that space has to be very flat. And it turns out that if it's flat now, in the past, it was even flatter. But that means that in the past, if you start off with it being not exactly flat, that gets amplified. And so the fact that it's flat now is actually an unusual and initial condition from the point of view of the Big Bang. So that observation is called the flatness problem. All those things kind of say, probably there's something going on in the past, which if we thought about it differently, would make those things seem like they were not unusual initial conditions. And so what I'm telling you now is the party line as to why, that there's a dynamical explanation for why all these initial conditions have the form they do, which is a very attractive one. And so there's varieties of this, but I'm going to focus on inflation as being the extrapolation that provides an explanation for all those things. This is a picture which I'm going to skip. It's just basically making the point that the fact that the temperature of the CMB is the same everywhere is a puzzle, because in the radiation-dominated universe, if you go right back to t=0, where time starts, there's not enough time in the history of the universe for the microwave background to know that they're all supposed to be at the same temperature, because there hasn't been enough time for light to get from one side of the universe to the other side of the universe to tell them all what the temperature is supposed to be. So that's kind of a puzzle. They all have their roots in this observation that things freeze when they're outside the Hubble scale, and the things we're looking at now in the past were outside the Hubble scale. So that means there's really not a lot of things, not a lot of dynamics that can explain what you see. And the way to solve that is to change the extrapolation. So just imagine that in the past, things were not radiation dominated all the time. So the kind of thing we're looking for is a change to the extrapolation, which changes the relative speed with which the Hubble scale changes compared to the size of physical scales. So we want the ratio of the physical scales to the Hubble scale, which is basically AH, that starts off now shrinking because the Hubble scale is growing faster. We like to have an earlier universe where it was growing instead of shrinking. But AH, remember, H is A dot over A. So AH is just A dot. So right now what's happening is that's shrinking because A dot is shrinking because the expansion of the universe is decelerating. So we're looking for a reason why the universe would be accelerating in its expansion. If it were to do that, then the ratio, what would happen then is that the physical scales would grow more quickly than the Hubble scale, and then that would change the way we would think about what's going on in the past. So that's what inflation does. It basically, if it were true that the Hubble scale were constant, and we know that it is true that it could be constant because we know that the vacuum could do that. That's an equation of state that would give you an exponential growth in the scale factor, so the Hubble scale is constant. If H were constant, then A would go like e to the HT, and then it's certainly true that AH is growing because H isn't doing anything and A is growing. And so it turns out that if something like this happened for where A grew by a factor of e to the 60, that would actually solve all the initial condition problems that we have. So in the inflationary picture, that's what we imagine is happening, is that if you extrapolate back, eventually radiation domination ends, and there's a period where something makes H be roughly constant. And what's happening when H is constant is that physical scales are growing more quickly, but then once H is no longer constant, they start to grow more slowly, and then they come back inside the Hubble scale. We can't do much outside here because things tend to freeze. But now you can explain what you're seeing here in terms of physics that's happening here is the hope. That's the inflation program. Now, you're trying to say, well, so you'd like to have a theory which makes the Hubble scale do that. And so you're trying to ask, what's the equation of state? What do I have to put in the universe to get that kind of behavior? Well, typically people put in scalar fields because they're easy to do, and they preserve things like Lorentz invariance for the backgrounds. And so the category of solutions that people use to try and engineer this kind of behavior in the past is they imagine they got a bunch of scalar fields, they design the potential energy for those fields, excuse me, to be such that at some point they're moving not very quickly. The pressure and the energy density of a collection of fields that are just functions of time turn out to be this. And so if I want to arrange that I have an exponential growth, that would be, I want to be close to the vacuum equation state, because that's what gives me exponential growth we've seen. Well, I can get the vacuum equation of state, which is P equals minus rho, if the kinetic energies here are negligible compared to the potential energies, because then these things are just doing what the vacuum would have done. They're saying that P is equal to minus rho. So the thought behind inflationary models is to arrange things so you've got a field that's moving very, very, very slowly, but not stationary, because you want inflation to end eventually, but it's moving very, very, very slowly. And so that in that region, the gravitational response will be to have the universe expand exponentially. Simplest models just use one field. And so we just have to choose V, and we're trying to make V very shallow. And the next few slides are going to quantify how shallow you want V to be to have this work. Well, the slow roll approximation is where you take the equation of motion for the field, which is this, the Klein-Gordon equation for a field in an expanding universe. And here's our Friedmann equation. And what you like to do is you'd like to approximate rho with V, because you want to say the kinetic energies are negligible. And you'd also like to drop this acceleration term. You'd like to have the fields just going to slowly track the potential. And so the approximation that we'd like to make is to drop the kinetic energy compared to the potential energy, and to drop the acceleration compared to, say, the force, the V prime term. So we like to make this approximation. That's when we should expect this inflationary things to happen, because once we have V dominating the energy, and once we have the field not moving very fast, then V is a function of the field, so it's also not going to change very much. It's going to look like it's constant, and that's the kind of thing we need. If V is a constant, then H will become a constant, and that's the thing we're looking for. We want to have an exponential expansion. So the way to quantify that, you see that the things we're looking for involve, if we use these equations of motion, we can take these and trade them for functions of the potential only, and they involve the potential, the first derivative of the potential divided by the potential itself, or the second derivative divided by itself, multiplied by factors of the Planck scale. So we're defining these two quantities, epsilon and eta, in terms of those derivatives that are dimensionless. And if they are small, epsilon is positive, eta could have either sign, but as long as they're an absolute value, they're small, then those two things we want to neglect would be negligible. And so we would expect inflation to happen if we can arrange for these two things to be small in some place in field space. And the nice thing is, this is all being expressed in terms of the potential, which is the thing you're getting to choose. Sometimes people, these are called slow roll parameters. Sometimes they're defined in terms of the rate of change of the Hubble scale and the rate of change of the derivative of the Hubble scale. And they're just related to these ones if you work through the equations of motion, the equivalent definitions. This other definition is useful if you have a model which is not built around the potential being flat. So it just is convenient for other uses, but you sometimes see it. All right. Now it's going to be useful to know that if it's true that we've satisfied our slow roll conditions, then chi is a function of the scale factor because it's a first order equation we're solving for chi. We do d chi dA. We can write it in terms of the potential, and the Hubble scale we can write in terms of potential. So we can integrate this equation to get chi as a function of A. We know A is a function of time, and so chi is a function of time. So we can treat time or the scale factor or the field as being proxies for time. And so, sometimes it's useful to think of the field as the variable because that's the thing that's easiest to use if what we know is the potential. So I'll use that in the next few slides. That connection between time, scale factor, and field. So here's an example of that. You can figure out how long inflation lasts, for example, in terms of the potential if you translate the number of e-foldings into an integral over the field because we use this change of variables from the field to the scale factor. So it just gives you an idea of how that works. And it shows you that that can be very large if epsilon, the slow roll parameter, which is a function of the field as well, is small, because that'll make this whole thing want to be big. So now there's some examples, but I'm not going to go through the examples because we only have 20 minutes left. So I'm going to just, there's 3 examples here that you can see in the slides. The first 2 are the ones that everybody always talks about, which I think they're well motivated, but they're not favored by the observations anymore. And then the third one is the one I think is the most promising one. It's the one that is equally well motivated, but it actually is smack dab where the observations tell you they should be. And I'd like to head towards, so I'm going to skip the discussion of the models to head towards the discussion of the observations. So the simplest one is just a quadratic potential. The next simplest one is sinusoidal potential, which is that's well motivated because that's a Goldstone boson. And so the corrections to the potential are naturally small. But the one that I think is the one that we're seeing in the sky is also a Goldstone boson, but for scale invariance rather than internal symmetry. And it has an exponential potential, but it actually has, this is just working through what the slow roll parameters are and when inflation would happen. And you can check the details if you're interested later on. So let me go back to the thread. We were, so that's all very nice. We can make the extrapolation change. And that's useful because now we can hope to explain what we see at late times in terms of what happened at early time, but we still have to do that. If we want to predict the primordial fluctuations, it looks like now we just have to push the problem back. We have to ask what happened in the inflationary period. And here's where the nice thing happens. So these models were invented for something else, to solve things like the flatness problem, but they give you a very nice description of the fluctuations for free. So let's go through this. So I'm going to make the argument that the prediction at the classical level is that nothing happens because inflation stretches the universe and it makes everything very flat and gets rid of all the fluctuations. So that what we should expect back here is that there are no fluctuations. So that sounds bad because it sounds like, well, then there wouldn't be any over here where we see them. But what happens is that because there's no classical fluctuations, quantum fluctuations are now the biggest effect. And there are quantum fluctuations. The quantum fluctuations are set by the Hubble scale, so they're constant. So they don't change. They just sit there and they don't go away. And because they're constant, different momenta that cross these 2 red lines are 2 different scales crossing the horizon. They have the same size as quantum fluctuations because h is basically constant. And so that means that we're going to get, if we follow those forward, we're going to get predictions for the fluctuations which are going to be independent of scale because they are each controlled each scale is controlled by the same value of h. So if h is exactly constant, there would be an exactly scale invariant prediction. It's going to sound like it's going to look like what we see, but it won't be exactly scale invariant because h is not a constant. And eventually inflation has to end. So it has to be that eventually h is changing and then inflation ends and it starts to do something else. So we should expect it to be almost scale invariant, but not quite. And so there'll be an explanation as to why the behavior at late times is not linear in k. It's k to a power, which is close to 1, but not exactly 1. It's a very, very pretty picture. So there's two parts to making that story. One of them is we have to track things through this region when everything's outside the horizon. That should be fairly simple because nothing much happens there. And then we have to ask what happens beforehand. So beforehand is what we call pre-horizon exit, and afterwards is horizon exit. Horizon exit is where the mode you're interested in crosses the Hubble scale during inflation. Now, I told you that things should be simple outside the Hubble scale. They are, it turns out. In these single field models, it turns out there's a quantity built from the Newtonian potential, which is time independent for small k. And small k is when you're outside the Hubble scale. And so the nice thing with that is that you tell me what this is at the initial time, I can tell you what it is at the final time just because it's conserved. And I don't need to know the details of what's going on inside here. So there's a very robust way of getting from the initial to the final time once we know what's going on in the initial time. And so I won't go through the details of that, but we'll just use that because it makes that part of it easy. And in the initial time, we have to kind of solve our equations again. And our equations we're solving are like the ones we were solving before. We have the metric coupled to some stuff. The stuff is no longer the fluid that we were talking about. Now the stuff is the scalar field that's driving inflation, but it's the same logic. We look at perturbations in the evolution. And so we'll have a bunch of equations like we had before. This is what they look like. These are no longer assumed to be non-relativistic. These are relativistic equations. But there's the field itself has a perturbation. And we have our Newtonian potential like we had before. That's still there. And then they're related to each other through the linearized Klein-Gordon equation. And this is the linearized Einstein equation that connects phi to delta chi. And you see that if the background had been time independent, this term would be 0, and this term would be 0. And if for that to be true, the potential would have to also have a 0 derivative. So this would be 0. So field and the Newtonian potential would evolve independently if we had a static background, or they wouldn't evolve, but they would be independent of one another. It's because the background is changing that the quantum field chi is mixing with the Newtonian field, which is constrained as a function of the other fields, in this place, chi. So that's the equation we're going to want to solve. And that gives you damped solutions, just like the other equations we've been looking at. And so this is why fluctuations are classically going away. If I had an initial fluctuation, that'd be like a wave. It's damped like crazy, but now A is not a power of time. It's exponential in time. So those things get wiped out super fast during inflation. So the classical prediction is that you should expect to see basically no fluctuations at all classically. But the quantum prediction, these are quantum fields. So the metric and the tensor part of the metric and the scalar field, they do fluctuate in the vacuum because the field does not commute with the energy. So like every other field in life, it fluctuates. And the fluctuation, if you calculate what it is in this geometry where the space-time has a constant Hubble scale, turns out to be proportional to the Hubble scale squared. They both are. It's kind of a very generic feature of quantum fields in that kind of a space-time. So whereas the classical prediction is 0, the quantum prediction for the fluctuations of the field is constant, essentially, if h is constant. And so what we have to do is track this constant forward through this frozen time. And we don't really want to know what the fluctuation, for the fluctuation of h, that's all we have to do. For the fluctuation of chi, we don't really want the fluctuation of chi, we want the fluctuation in the Newtonian potential, because that's what we measure at late times. So we have to track the fact that the Newtonian potential is constrained in terms of delta chi and inherits fluctuations from chi. And so because of that, it's going to care about the time dependence of the background. So there'll be a slightly different dependence on the amplitude of the Newtonian potential won't be controlled just by h. It'll also care about how fast h was changing. And I'm just going to quote you with the answer for that because we're down to 15 minutes. And this is what you find. So for the Newtonian potential, it's proportional to h squared, but it also depends on epsilon, the slow roll parameter, which is telling you the deviation, how fast things are rolling. And that's because you had to get the quantum fluctuation from chi into the Newtonian potential. But for the tensor mode itself, it's just proportional to h because it's just that mode is fluctuating, and you just watch how it fluctuates now, given that it was fluctuating in the past. That's what I told you. Now this ratio R is the ratio of the one to the other. The claim is that this is what we've seen already in the microwave background, and people look for these fluctuations and have not seen them yet. And so the way they quote the absence of seeing them is the ratio is an upper bound on the ratio is quoted. And that's what that variable R was that we saw before. But you can kind of see that that ratio is controlled by the slow roll parameter epsilon because of that difference between the dependence of these two amplitudes. We can also calculate the spectral index, this NS that was appearing when the answer was K to the NS in the density perturbations, and K to the NS minus 1 for the Newtonian potential. What we need to do is we need to take our answer and differentiate it with respect to log K to get the NS minus 1 in this case. But we can do that because K is determined by any one mode with given K crosses the horizon at a specific time. But we know that time is tradable for scale factors, tradable for field. So what we can do is we can trade derivatives with respect to K for derivatives with respect to the field using the change of variables that I showed several slides ago. That's what that turns out to be. And so since we know what delta is in terms of epsilon and h, which are both functions of the fields, it becomes very easy now to do the derivatives and see what this prediction is for ns minus 1. And this is what it turns out to be. It depends on the two slow roll parameters, epsilon and eta. Excuse me. There's a similar story for the tensor modes, that if you imagine that they go like k to a power, this is what the power would be. So the bottom line is you get a prediction for the scalar modes, that you get a prediction for the amplitude and you get a prediction for the power, ns minus 1. This is the prediction. And there's a similar prediction for the tensor modes. They have an amplitude and they have power. And the ratio of those two things is controlled by the same variable that gives you this power. So you have three parameters in your problem that are predicting everything: the Hubble scale during inflation, the at horizon exit, and the two slow roll parameters, epsilon and eta at horizon exit. And those three things are giving you four variables, the amplitude and the tilt, or the spectral index for these two kinds of fluctuations. And so there's a prediction. The prediction is that n sub t is minus r over 8. That has to be true for any of these models. And all that goes into this really is that they involve a single field. The different single field models will give you different predictions for what epsilon and eta are and what h is. But the fact that there's only these three variables in these predictions is true for all of them. And this is how they do. So here's the end of the cosmology section. Here is a plot of what Planck, this is the vertical axis is that R, the tensor to scalar ratio. And across the bottom is NS, the value for NS that's consistent with what you see. And here's where you're allowed to live. Shows you that there's an upper limit to R, and then there's a preferred value for NS, which is around 0.97. And these are the various models we're looking at. And the three models I kind of selected out and skipped earlier on. Their phi squared model is this prediction here. It turns out to be these dots there. So those are not very good description of the data anymore. The oscillatory model, the trigonometric thing, is this purple swathe. There's a parameter in the model which you can change that makes it, in one region it looks like the phi squared model, but in other regions it's different. And again, it's not such a great fit to the data. But the exponential potential model, the one that I think is actually very generic, here it's called alpha attractors for historical reasons, that there's a particular class of models which agree with these in a particular limit. But that's the way the observers chose to present their data. That's what these yellow lines are. So those are smack dab in the middle of where the measurements are. So when I tell you that those models are, they look better than the other two, it's because of that the observations like the choices that are being made for ns minus 1 and the tensor fluctuations better. Okay, that's a natural time for questions if there are any questions. I'm going to have a very quick final effective field theory section, but I'm just pausing here because this is a natural break point. And I've been talking solidly for a while now. That's a beautiful story. There's a very, very organic picture of where galaxies came from and where the initial conditions of the later universe came from in terms of changing having an earlier accelerated period of expansion. And the fact that that's accessible to observation is a remarkable thing. And if this picture is right, that quantum fluctuations are what you're seeing, it's even more remarkable because it's saying that not only are quantum gravitating effects possible, and they could be large enough to be seen, they have been seen, is the claim. And so the last part of the lectures is to do with quantifying the errors in that, because we really have to understand how big quantum effects are in gravity for that whole thing to have made sense. Okay.
I have one question. So do you
Yeah.
have any comments on some super-Planckian nature of large field inflation?
So there's, I do at the very end, I have a list. I kind of took all of the various issues. I put one slide where I kind of go through them all, and I show you, I just say in yes, no form, my take on them. But so the question that for the rest of the room, it's been argued that in this inflationary story, modes are being stretched and become very large until they're across the sky. And if you look at the modes that you're looking at now, and you ask in the past, where, you know, how long were they? The observation has been made that in the not so long ago in the past, they were smaller than the Planck size. And that raises the question, as that's a problem or not. Or sometimes people say it's an opportunity, but it makes it sound like you need to understand trans-Planckian physics in order to make these predictions. And I think that that's not a problem. You can make a universe where it is a problem, but it's generically not a problem for the same reason, because the issue is essentially, that's what effective field theories tell you, is that this is not a gravity issue. This is a time-dependent field issue. If I have a magnetic field in the lab with no gravity, and I look at Landau levels, whose spacing is set by the size of the magnetic field, and I turn the field off, so all those levels collapse. If I take any finite energy after the field's been turned off, that mode came from above the Planck scale. And so the same issue that happens in inflation also happens whenever you turn a magnetic field off in the lab. So if you really thought it was a problem in inflation, you should also worry about it in the lab. And the reason it's not a problem in the lab is that as long as the modes come in their adiabatic vacuum, it doesn't matter what happens. Nothing depends on those modes as long as they're in their adiabatic vacuum. And so you could set things up so that they're not in their adiabatic vacuum, and then it would make a difference when you turn a magnetic field off. But generically, they are in their adiabatic vacuum, and that's the generic thing that happens, and it's not an issue. So it doesn't matter that those modes came in as long as they come in the vacuum. And the same thing's true in inflation. So my attitude on that is that the trans-Planckian problem is a myth, it's a mirage, and it's because people have not been very careful about thinking about effective field theories and how the same effects happen outside of gravity, which gives you a lot of intuition for how things, what's a problem and what's not a problem. So that's my take on that. It's a good question. So let me very quickly, because I can see that we're now down to the last 7 minutes. I will cherry pick through the main things for effective field theories here, because I have too many slides, and we won't get through them all. So the theme is, the first part, I want to remind you about quantum effects in gravity. Why do we have control over them? We do, as long as it's long wavelengths. And you'll see that that's, in cosmology, requires the Hubble scale to be smaller than the Planck scale, but it is, so that's not a bad thing. The second thing will be, cosmology adds to gravity things like scalar fields, and that it turns out to complicate the argument as to how big quantum corrections are. So I'd like to point out how it complicates it. And then the third thing is, I was just going to go through various issues, including this trans-Planckian problem, and just tick off. There's a take you can have on them based on this picture, but I'll just tell you what the take is, and that's mostly to suggest places for you to read in the literature where those takes have been made. But the organization of the thinking is along these effective field theory lines, which I think is the only systematic way we have for thinking about these things. So for gravity, we've already talked about some things about gravity, that the basic symmetries of gravity are dictated to us by Lorentz invariance and quantum mechanics. And if you do perturbation theory with gravity, what you do is you just take the metric and you expand it around some background metric. In this case, I'm taking flat metric, but you could take a cosmological metric, take your favorite metric. And what happens is that because the Einstein action involves two derivatives, you get all possible powers of fields but only 2 derivatives for any of the interactions. And the more fields you have, the more 1/n Plancks you have. It's essentially that's the structure. It's a complicated structure, but it basically, what's important about it are those 2 facts, 2 derivatives and 1/n Planck for every additional field beyond 2. And if you look at graviton scattering, we can do the same power counting that we did for the toy model using this kind of a Lagrangian. And what it would tell you is that this graph has a 4-point interaction, so that's this thing. It should be proportional to the momentum squared. And this graph should have 2 interactions, so it should be proportional to momentum to the 4th power, but the propagator goes like 1/n momentum squared, so they both should go like momentum squared. And so you'd expect this thing to go like momentum squared divided by m Planck squared. In this case, it's the interaction has a 1/n Planck squared, and this has 2 interactions, each of which goes like 1/n Planck. And that's exactly what you get. If you do the full calculation, you get this, where S, T, and U are the Mandelstam variables for the scattering, and G is 8 pi G is 1/n Planck squared. This calculation was done by DeWitt in the 60s, but you see that the power counting from these Feynman rules gives you that answer quite well. And of course, the problem with quantum gravity doesn't come at classical tree level, it comes at loop level. And the loop level, the problem is that because all those derivatives and the interactions, the loops you get when you take a loop amplitude for the corrections to the leading part, you find integrals that are diverging like crazy. And in particular, here I focused on a piece, these depend on the external momenta, Q, and I'm focusing on the piece which goes like Q squared, just because that's what also appeared in the tree level answer. Those kind of divergences can always be absorbed into the Newton constant, because in that tree level example, the answer was proportional to Newton constant. So a divergent coefficient with the same momentum dependence can also be absorbed into that. So those are renormalizable in the usual sense that quantum electrodynamics is renormalizable. But the problem that you get with gravity at the quantum level is that you get also things that are not quadratic in Q. You get things that are quartic in Q that are still divergent. So things like this, the corresponding integral that goes with the Q to the 4th term goes like d4p times p to the 4th over p to the 8th. So that's still diverging. And those are things that you can no longer renormalize into Newton's constant. So that was traditionally the problem that people had with quantum corrections in gravity. And of course, the next slides are just emphasizing that that's not a good enough picture, because we're doing measurements, comparing them to theory, and the agreement requires the theory error to be small as well as the experimental error. And that's true for gravity as well as it is for quantum electrodynamics. And it only makes sense to compare classical calculations of gravity to observations if we have a quantitative assessment of what the size of the quantum effects are. And that's something which people did not have in the 60s. But we now know we should think of this as an effective field theory. We should think of the Einstein term as one piece in a derivative expansion where we have all kinds of other things in it, much like the toy model. And all you need to know for this is that each power of curvature you have involves 2 derivatives again. So the Einstein term had 1 power of curvature, but additional powers of curvature give you more derivatives, because the curvature is a derivative of gamma, or the square of gamma, where gamma is again a derivative of metric. And so you can go through and do the same power counting that I did for the toy model for the theory of gravity. And this is what it tells you. It tells you that an amplitude with E external lines and Q being the external energy depends on the number of loops and the number of vertices in this particular way. Little m here is the thing that appears in curvature cubed in higher terms. M Planck is what's in front of the Einstein term. And everything else 4 pi is 4 pi. And the dimensionless coefficients, these C's are dimensionless. I'm not keeping track of them. I'm just keeping track of the scales. So the logic is as like before, the things that are in the couplings, we can keep track of explicitly from the Feynman rules. And then on dimensional grounds, I tell you what the Q dependence is. And then I use some identities like the conservation of ends and the definition of loops to trade the number of internal lines, say, for the number of loops and things like that. And so you can write it in this way. And what's nice about this is that this tells you something interesting. It says, well, if I want to know the dominant contribution to graviton scattering, what do I have to do? I have to make this thing as small as possible. The first thing is that Q's are always in the numerator here. So this expansion is a good expansion if Q is smaller than all these other scales in the problem. So that means a low energy approximation will control things, and that makes sense given that a derivative expansion looks like a low energy approximation. This biggest term will be make the number of loops 0, and then make this thing not contribute. This involves a product. K here is the number of derivatives, and I is the number of fields. So the fact that this is bigger than 2 means this gets contributions only from interactions that are curvature squared and higher. It doesn't get contributions from the Einstein term. So the way you get the dominant contribution to something with E external lines is work to no loops, that's tree level, and include only the 2 derivative interactions, which is to say general relativity. So that says what you probably believed anyway, is that the dominant contribution is classical general relativity. Sorry, that's my timer. And I'm just about done here. I can see that the time is 9:20, and I'm just going to be finished in a second here. This tells you the general relativity is the dominant piece, but it also tells you what the corrections are. And the corrections are 1 loop or tree level with 1 curvature squared term, and the divergences in the loops are being normalized by the curvature squared term. So there's a very systematic statement here. And the message is the reason classical general relativity works is because of the low energy expansion. So Q over M Planck is what controls the low energy expansion, because that's what controls the loops. That's the loops are factors of H bar. The scale M here, a question was asked in the first lecture, what scale goes here, the biggest or smallest? One way to think about this is imagine you have a theory of the world, you calculate what these coefficients are by integrating out some particle of mass M, then you'd get a correction to this, which goes like M squared, you get a correction to this, which goes like log M, you get a correction to this, it goes like 1 over M, and then you should be summing over all the particles in your problem. And a sum of 1 over M squared over all masses will be dominated by the smallest mass in the problem, and the sum of M squared over all masses is dominated by the largest mass in the problem. So you should think of this M being the smallest mass that you've integrated out, could be the electron if you're doing cosmology. And this is the biggest mass that we know about, which is the Planck mass. And it's a very attractive picture, which I won't harp on. I want to just say what's different when you do the same thing with scalar fields. So we imagine having scalar fields with derivatives as well, yada, yada, yada. We get to the power counting, it's the same story. There's the loop counting parameter, which is controlled. In this case, I'm writing the external momentum as being H now because I'm interested in cosmology. That's the external derivatives. Things involving 4 derivatives or more are suppressed like they were before, so there's no change there. The 2 derivative terms are not particularly suppressed, so there's nothing that forces you to linearize general relativity just because you're at low energies. Nonlinear general relativity is not suppressed at low energies. But the interesting thing is that the 0 derivative terms, which is the things that we didn't have in general relativity, they involve H's in the denominator, not the numerator. So those are dangerous from the point of view of the low energy expansion. But in inflationary models, if it's true that the potential energy is what's giving you your curvature, there's a relationship between the Hubble scale and the V, which is the potential, that's the scale in your potential. And the Hubble scale would be the potential divided by M Planck squared, and that makes this ratio 1. So for inflationary models, where you've designed these potentials such that the Hubble scale is controlled by the scale and potential, these dangerous terms are not there. So that in that particular case, you're safe. And that's the main message for scalar fields is that they can be dangerous because non-derivative terms, higher derivative terms are suppressed. 2 derivative terms are basically, you can have as many as you like because that's relativity, but no derivative terms are enhanced at low energies. And so they're generically dangerous. You have to check if they're okay or not. In inflation, they are okay. If your external scale is the Hubble scale. So now my last telegraphic thing is now going through issues like trans-Planckianism, just to give you a take on what this effective field theory thing says. Were time-dependent backgrounds a problem? We've already talked about that. That's a no. That's not a gravitational issue. That's something which you can do for non-gravitational fields. Inflation, in the examples I showed you, to get slow roll, you need fields that are actually bigger than the Planck scale. Is that a problem at low energies? It doesn't have to be. The issue is whether or not your potential gives you a lot of energy for large fields. If your potential is shallow enough that large fields are not large energy, there is no problem with having large fields. The question that was asked was, is there a trans-Planckian problem that modes that are above the Planck scale come below the Planck scale? And that's the answer is there's not a problem there, and it's also not a gravitational problem if they're adiabatic. There's a whole naturalness issue story, which if anyone asks about it, I can tell you my take on. There's a lot of, in the literature, people worry about higher derivative terms in effective theories, and they talk like you have to be careful about excluding them. And that's not true. The ordinary fields that make perfect sense can have higher derivative terms in the effective theory, and there's a reason why that makes sense. There's a problem calculating numerically with effective theories, which hasn't been solved yet. There's a way you can use effective theories at late times, which is also being worked out now, but it hasn't been, it's promising, but hasn't been finished yet. And there's a very beautiful formalism for capturing the physics of inflation specifically, because that's a very Goldstone mode-like behavior, and with having one scalar field give you cause the Hubble scale to change is a very situation where the symmetries control a lot of what the predictions are. And so there's a very beautiful picture of that called the effective field theory of inflation that is worth reading about if you're interested in effective field theories in inflation. So I'm coming down to the wire there. There's 5 minutes for questions, and this is where I would stop. And I apologize for being so brief in these last topics, which are really a subject of lectures in themselves. But I thought it was more important to really focus on the fluctuation story, because that's the observational side of things that driving the interest in this area. So thank you for watching.
Okay, thank you very much. Any questions?
Yeah, I kind of have a naive question around. So basically, in let's say the inflationary picture, you talked about these modes that are like freezing out in super horizon, and that will basically be connecting, let's say, the quantum fluctuations all the way up to the physics that we now observe, like in the CMB. But this is because we are considering like slower inflation, right? I mean, what if will this argument actually hold if there is some kind of process that is basically giving like a super horizon evolution? Let's say, okay, if there are like more fields in this era, will this same picture hold?
It depends on whether some parts of it will, some won't. So I would say that the generic observation that it's difficult to get dynamics to do something useful for you, that's super Hubble. That's more generic than the single field statement. That's for multiple fields. It's also true, but what you're alluding to is also there's an observation that the strict conservation of the curvature perturbation, the zeta that I had in my slides, that is a specific feature of. Sorry, I'm just trying to get back to my slides here so I can. So if I go back to the part about the conservation of zeta, that what you're alluding to is true, that if you have multiple field models, then the curvature perturbation is not strictly conserved, and so there is more interesting dynamics. The ability to predict what happens here, given what happened here, gets harder. But it's not the same thing as saying that the physics of the super Hubble modes in here, you can do anything you want, like you could have done if it was sub-Hubble modes. It's still true that super Hubble modes are very strongly constrained because of basically the speed of light is limiting what can happen on scales that are that large. So the difficulty in explaining things without coming back into super Hubble region is always a difficulty, even in more complicated models. But the more complicated models introduce more complications also in making the prediction, in predicting how things evolve, even in the super Hubble regime, because it's not quite so simple as saying that something like zeta is conserved. So now it depends on exactly the question is that the thing you're trying to calculate, whether it's controlled by the physics, multiple field physics outside the Hubble scale, or if you need something even more complicated going on at sub-Hubble regions.
And related, like just going on with this multiple field thing. So at the end you mentioned, let's say, effective field theory and inflation. Well, and so this is also, let's say, a general statement if you just like put like multiple Goldstone modes, if there are additional fields that are contributing into this inflationary scenario. So is the EFT of inflation generically extended up to, let's say, n fields at the era?
I didn't hear the last part. Extended up to what?
extend up to like multiple fields. Let's say.
I think various people have tried to do it, but I think they've found that it hasn't been so useful. So the power, I didn't describe effective field theory of inflation, and for those who haven't read about it, the what's going on there is in this, in the toy model we did, the low energy limit was very simple because the low energy field was a Goldstone field, and basically all of its properties at low energies were being dictated by symmetries, and so there wasn't a lot of model dependence in that first term because symmetries, if we'd done a non-abelian version of it, it would have been equally constrained. The symmetries are telling you everything about how the Goldstone boson behaves. But if you have other fields in addition to the Goldstone bosons, then it's model dependent how the other fields enter. And the story in inflation is like that if you have a single field that's describing, de Sitter space is very symmetric, so there's no unique way of slicing it to decide what your time direction is. But once you put the perturbations in, you have the rolling, that's the deviation from de Sitter space, is giving you a preferred frame. And so it's the thing that as long as there's only one field doing that, the features, the deviation from the symmetric de Sitter limit are very Goldstone-like, and so they're dictated largely by the symmetries. And so then you have all the simplicities that happen with Goldstone bosons happen, and that's kind of the utility of the original proposal. But once you add other fields, you're now in that model-dependent regime where the other fields are not uniquely determined by the symmetries, and so then there's a lot of choices you get to make. And I think what they found in the inflationary case is the analog of what you find in particle physics too, that it becomes because it becomes model dependent, it's less useful in the sense that it's not giving you universal statements about what you should see.
Thank you very much.
So you can do it. You can certainly do it, but it hasn't been as useful as the single field case has been.
In any case, it sort of loses its own original philosophy of these unique predictions, and it becomes into a very model-dependent regime.
Yes, and that's what you would expect, because it's once you add more fields, the symmetry is not enough to dictate what all the fields are doing anymore, unless you add more symmetry.
Okay, thank you very much.
Good question.
Any other questions? Could you? I have one simple question. Could you show the last slide, please?
The very last one, okay.
Then,
That's right. That was farther than I wanted to go. Sorry. Sorry, let me just put the slide back on. What happened is that it's completely bailed of the slideshow. Let me just, here we go. All right, now we're back. Now I gotta. And that'll do.
yes, thank you. Yeah. So here you mentioned that the Ostrogradsky ghost
Yes.
is not a big problem. Could you say more why you say so? Yes.
Yeah, so what I have in mind here are things like the people write down things like the Horndeski Lagrangian, and the logic that is used for that in cosmology is people make the true statement that if you for those who don't know, the Ostrogradsky ghost is if you write down a Lagrangian involving more than second derivatives in time, then it's a very generic property that your theory is unstable, because if you calculate the Hamiltonian for that, it's linear in one of the variables. So it means it's never bounded from below. And so it's very general that if you have higher derivative in time theories, that the classical behavior has runaway modes and is unstable. And so and that runaway mode is what they mean by the Ostrogradsky ghost. Now, so based on that, people often in the cosmology business say, well, let's look at higher derivative theories that have the property that they do not introduce higher time derivatives into the equations of motion. And those have been classified, and those lead to the Horndeski models.
Right.
But the point of view that is behind that is that you need to protect yourself from more generic behavior, because the Ostrogradsky problem would be a real problem. But from the effective field theory point of view, we don't have to do gravity. We can just talk about an ordinary non-gravitational system. you could ask the same question. If I have a microscopic theory, say a heavy field and a light field, which is all two derivatives, so I know that there's no runaway modes at all, and I integrate out the heavy field to get the effective theory for the light field, is it true that I don't get these higher time derivative terms in the effective theory? And the answer is no, it's not true. If I look at the effective theory I get for the light field, I get all possible terms, including arbitrary time derivatives. And so then you might say, well, so then why isn't there a problem there? Because the full theory has no runaway behavior, but the effective theory seems like it should because it has these higher derivative terms. And the answer to that is that the effective theory is not, the theorem is not that the effective theory, that all of the solutions to the effective theory are not capturing solutions to the full theory. The statement is that the effective theory only captures the time evolution that is perturbatively small, like in powers of 1/m compared to the full theory. And if you look at the runaway modes in the effective theory, they all go like e to the mt or something like that. So they're not perturbative in 1/m. So the apparent sickness in the effective theory is actually outside the domain of validity of the effective theory. And so there's no requirement in the effective theory to get rid of these dangerous higher derivative interactions, because if you treat the effective theory self-consistently, they don't give you any problems. And so that because of that, I think it's misguided to say if you're writing down an effective theory, the need to protect yourself from these higher derivative modes by thinking of in terms of Horndeski models is not necessary, because the effective theory itself protects you from those things, and those interactions usually are there, but they just, if you treat them within the effective field theory, they don't cause any problems. But they may have physical predictions which are worth understanding.
Could you, when you send the talk file, could you also give some references on these issues, which I did not know very well?
Yes, I probably this.
Cosmology, ghost, and the higher derivative theory. Yes.
You know, I have there's one specific reference I could probably give you right now in real time. But I'll, maybe the simplest thing, I'll put it in the slides, because that's easiest to get to, and you'll know where it is.
Yeah, there is another question from the Zoom audience. Liliana, please.
Yeah.
Yes, maybe I was lost in what you said about this comment on technical naturalness. Could you explain that in terms of the EFT, because I didn't get the point.
Yeah, you didn't get the point because I didn't really get a chance to make the point. I just kind of, as I went by, I said that if anyone asks, I can say something. So thank you for asking. So I only put that one in there because naturalness arguments is in quotes there, because there's many different things that are called naturalness arguments, and some of them are just aesthetic. You know, that if you one version of naturalness is that if you have a number that's bigger than 1, then you need to explain it. And I think that in the end of the day is an aesthetic criterion, which effective field theories have nothing to say about. But there is a specific version of naturalness called technical naturalness, which effective field theories do have. And I think that for cosmology is very useful in the sense that, so technical naturalness is a statement that if I have a small parameter in my problem, and that might be a ratio of scales. So let's say it's the size of a nucleus divided compared to the size of an atom or something. That's controlled by some parameters in my Lagrangian, but there's some small dimensionless thing in my problem. A small thing is technically natural if the way it's explained, why it's small, it's explained in some high energy theories tells you why it's small. But then as I integrate out all the physics down to lower energies where I measure that parameter, it stays small. That's what it means to be technically natural. And so the smallness of a nucleus compared to an atom has that property. If I ask in the standard model, why is an atom small or big compared to a nucleus, it's because the QCD scale is bigger than the electron mass and the fine structure constant is small. But if I integrate out QCD and I just talk about the theory of protons and electrons, there's still an answer that in this case now the proton mass is larger than the electron mass and the fine structure constant stayed small when I integrated out the QCD. And so in that sense, the smallness of atoms is, or smallness of nuclei is technically natural. And the thing is that every hierarchy that we know about in nature, and we know thousands of them, they're all technically natural in that sense. That the effective field, the message of effective field theories is that it's not like there's one classical action that is true, and then we quantize it. And you have to ask, why is that one classical action parameter small? Really, the idea is that there's as many actions as you have scales. So, you integrate stuff out and you've got effective theory that describes your physics at any scale. And none of them is more important than the other one. And anything that's small should be understandable in all of them. You shouldn't have to choose which one you get to ask the question in. And that's just an experimental fact that all the understood hierarchies are small in that sense. And so when we talk about things like cosmology, the things that tend to be not technically natural are things like small masses for scalars or small vacuum energies for scalars. And what's kind of interesting is that cosmology loves those things, right? Many explanations of dark energy rely on very, very light scalars and very, very small vacuum energies. And those are extremely hard to get in the sense that normally if someone predicts you a small vacuum energy or a small scalar mass at high energies and you start integrating out physics, then the physics you integrate out actually gives you large contributions to those things. And so the only way you can actually arrange something to be small where you measure it is to have actually a very large prediction for the vacuum energy at high energies, which just exactly cancels all the integrating out you had to do to give you the small thing that you measure. And it's logically possible that nature works like that, but there's never been an example that we've understood where it works like that. So from the point of view of cosmology, I think that's a super useful clue, because if cosmology is at the longest distance possible, and it seems to be pointing to the success phenomenologically of things that are extremely difficult to get from high energies. And we're never going to have enough cosmological measurements to distinguish all the models of dark energy, for example. But that doesn't matter, because that's not all the information. Part of the information is that cosmology is the low energy limit of stuff that describes everything else in nature. And this technical naturalness clue is probably the most important one, because the ones that satisfy that clue, so that's the theories that could have arisen as the low energy limit of something more fundamental, they will be more restrictive than the generic theories. And then all we have to do is distinguish amongst those. And so that's an important part of finding the solution, I think. Now, the reason that everybody doesn't necessarily agree that that's true is in things like the cosmological concept problem, there are no examples of things that do work. So it's not like we have a working example where we say this solves the problem, and so this is the one you should be testing carefully. But that doesn't mean that they don't exist. And so I think that technical naturalness, I think, is something which is almost certainly, it's very conservative to assume that it's true. And it's a very useful way to guide your thinking of what the physics should be that's describing these things that in cosmology don't want to be technically natural. And so it's crazy for us not to use that information, I think.
Liliana, I cannot hear you. Please unmute.
Oh, you're muted, Liliana.
Yeah, sorry. No, I was saying that the same could be applied to theories beyond the standard model, that you can classify all these BMSM models in terms of which one have the naturalness, technical naturalness embedded.
In that case, you're right that was actually the organizing feature for most of the models. That the logic of that was that in order to solve a naturalist problem, you have to change physics at low energies. And then what's nice about that is that it suggests things to look for. So it's a way of proposing alternative theories where you don't have any experimental guidance. It's a way of suggesting proposals that will be testable. And so almost all the things that people looked for, things like composite Higgses or supersymmetry or large extra dimensions, those were all technically natural. And that's why they were pursued, is that they did satisfy this criterion of explaining why the Higgs mass could be as light compared to the Planck scale. And one of the arguments against technical naturalists is that all those proposals weren't seen. and in that particular case, I think it's really, in my opinion, it's kind of one of those things where we don't know that it's failed, in the sense that it's true that the simplest things that would have been spectacular weren't there. But it's also not true that it's also true that you could have natural solutions which you would not have seen yet. And so part of the story about cancellations is a question of how much of a cancellation do you find unacceptable? So if the cancellation involved is 1 part in 1,000, does that bother you? Or some people it does. For me, it doesn't really. But if a cancellation is 1 part in 10 to the 120, then most people are bothered by that. So in the Lecture weak case, the cancellations involved depend on the theory, depends on how high the scales were. And I think it's really the jury's out as to whether or not the solution to the whatever is beyond the standard model is technically natural or not. But it's certainly been true that thinking in technical naturalist terms was very productive in producing lots of theories which could be tested and found not to be there in that case, but they were predictive in that sense. So it was a very fruitful research strategy. So my personal take is that the two things that people worry about for naturalness are the cosmological constant problem and the electroweak hierarchy problem. Electroweak hierarchy problem, I think, is a bit of it's a hung jury in the sense that we don't really know what happened at those energies, and there's many things that could happen that are natural that we wouldn't have seen, so we don't really know what to say there yet. The cosmological constant problem is a harder one because there the electron is the problem. So you're at such low energies that you can't just fix things at energies we haven't seen. And the absence of a solution in the cosmological constant case is more worrisome because that's at energies where we think we really should understand things. And if there are no solutions that are natural, that would be a problem for this whole picture that I'm trying to sell you, that technical naturalness should be important.
Thank you.
Good question.
Any other questions? I don't see any more. So let's thank Professor Burgess again for his wonderful lectures. Thank you very much.
Thank you very much for the invitation and the attendance.
Yes.
Thank you.
Bye.